Okay, the final talk of the session will be by Juan on the role of the magnetic field in the formation of density structure in molecular clouds as revealed by dust polarization.
Can you guys hear me? Yeah, it works? Okay, so I know I'm standing between you and your coffee, so I'll try to be brief, and I'll show lots of pretty pictures. So yeah, I'm Juan Soler. I come from magnetic France, I guess, and I work on the data analysis of the Planck data. So this is pretty much a view of the role of the magnetic field in the formation of molecular clouds as revealed by Planck. So we can begin with this slide. It's worth remembering this. If you look at some millimeter polarization, so in this case, those slabs correspond to the plane of oscillation of the electromagnetic wave, of the electric field of the electromagnetic wave. So if you look at the starlight polarization, you're looking at the direction of the field. If you look at some millimeter polarization, you're looking at the direction perpendicular to the field. And you're measuring the field integrated along the line of sight in the places where there is dust that is aligned with the magnetic field. Okay? So with that caveat, let's go to the pretty pictures. So first pretty picture is this one. So this is from a paper that we just submitted, and I'll put in the archive at some point very soon. And here, the wrinkles, those wrinkles that you see there, that is the direction of the magnetic field as inferred from the Planck observations. And those whiskers that are around there, those are starlight polarization observations. Okay? Those are not all of the stars. Actually, we have 9,000 stars in this region. But if you put all of the stars, you just see a black, blurry thing. So I just took a vicinity of 3 arc minutes in diameter, and I averaged the mean direction of those stars, and that is the orientation that I get. Okay? So to make a long story short, we find very good agreement between starlight polarization and the sub-millimeter polarization. Okay? So why does this guy has a cow in his presentation? Well, I'm going to be comparing simulations and observations. So if you're the kind of person that gets a little bit nervous when you start seeing pretty images from simulations and observations, just look at the lower right part of the screen, and if there's a round cow, it means it's simulations. And if you see a real cow, that means it's observation, okay? So if you feel lost, you just look at the lower part of the screen, okay? So the way we did this analysis of relative orientation with Planck was very particular, because first we look at the simulations, and then we look at the observations. So we were not trying to test if the simulations were actually reproducing reality. We're trying to test which are the right questions to ask, okay? So when you have the simulations, you have only a few parameters that you can play around with, and then when you have the observations, you have everything, even stuff that you don't know is there, okay? So with the simulations, we try to look for a tool that would tell us the relative influence of each one of these 3 parameters. And in particular, we wanted to see what was the role of the magnetic field in the formation of these molecular clouds, okay? So we simulated 2 molecular clouds, one that has a strong magnetic field with respect to turbulence, and one that has a weak magnetic field with respect to turbulence. And those are those 2 up there, okay? And what we found is that if you test the relative orientation of structures, not filaments, we just use the gradient, we define the isocontours of column density, or density in 3D if you want, we see that if the magnetic field is dynamically important and is at least as strong as turbulence, there is a change in relative orientation from mostly parallel in the less dense stuff to mostly perpendicular in the most dense stuff, okay? So I think I jumped too fast. Oh, I have this, okay. Okay, this doesn't work, so I'll just go ahead. So this is in, okay, well, this is in 2D already, but remember, if the magnetic field is dynamically important, there is a change in relative orientation. So we went and we thought that was a good question to ask, and then we asked that question in the Planck data. So this papaya diagram is just basically the column density, the dust column density, as the gas column density as inferred from the dust opacity, okay? So you just do a gray body fit to the Planck data, and then cyan and blue correspond to less gas along the line of sight. Red is a lot of gas along the line of sight. And on top of that, we took the directions of the magnetic field that we inferred by just simply rotating 90 degrees the direction of the polarization at 353 gigahertz. Okay? That's all we did. And then we overlapped that. And those are the nice maps that we have been producing, okay? So you can learn a lot about these maps. And if you ask people, you can learn about their political positions or their general views of life, but you won't learn much physics unless you know exactly what you're looking at. So that's what we try to do. So this is another projection that maybe you haven't seen. So remember, total gas column density inferred from dust opacity, and then the direction of the magnetic field. And of course, I picked this one for Carl because this is the Eridanus bubble. So when you put together the Eridanus bubble, that is also a bubble in magnetic field. Okay, so when you take all of the sky, and then you do a selection of points of interest, and then you check what is the change in relative orientation with increasing column density, you see that most of the less dense stuff, here is the column density from 10 to the 20, and so on and so forth, are mostly parallel. And as you increase column density, you lose that alignment, okay? Until you arrive here to molecular territory, okay? This is the result that Elisa Goodman was quoting on Tuesday, that you go from mostly parallel to undecided, okay? So what I did was make a zoom in into these column density ranges in objects that we know. So I took this map, I already told you how we did it, with polarization, and then I picked 10 objects that we know very well. These are, some of them are Gould clouds, but these are all molecular clouds which are within 500 parsecs from us. And they look like this. And then I asked the question, what is the change in relative orientation? And I found that for those 10 objects there, there's a change in relative orientation from mostly parallel to mostly perpendicular. So I've been showing these diagrams. Some people have been showing the histograms. This is a parameter that tells you if it's positive, it's mostly parallel. If it's negative, it's mostly perpendicular, okay? When you have two vectors in 3D space and you project them, most likely they're going to show parallel. If you have these two vectors and they're perpendicular here, and I show them to you like this, they are parallel. They're parallel like this. The phase space for parallel is very large. But if they're perpendicular, there's only a few projections where I can show them to you where they're perpendicular. Well, if they're parallel, they look parallel in many configurations. So this is statistically significant, and I can tell you more about that if you ask me. So this is the result that we have. So mostly parallel, mostly perpendicular, but I don't want to focus on the result now. And we gave an explanation in the paper, and many people, including Basu and many of the speakers in this afternoon, have been telling you what is changing here. But I'm going to tell you about the stuff that we want to continue searching. What is missing in this result? So we know here we can have something like flows that go along the field lines, and then you accumulate matter by gravity. So most likely between here and here, you have the onset of gravity. You start accumulating matter by gravity. But there's also many interesting things that are happening at that particular set of column densities. Alex mentioned magnetic reconnection. Isabelle Grenier was mentioning the change in the ionization rate. There's a scaling of the magnetic field strength that was shown by Tom yesterday. And there's also a change in the dust properties. So we want to check this with in other regions and with other traces and see if what we're finding is reasonable. So that's what we did in Starlight. So just so you get an idea of how Starlight works, well, when you get the polarization from a star, you're sampling the interstellar medium between you and that star. And the size of your observation, the resolution of your observation, is basically the diameter of the star. While when you have Planck, Planck is a cosmology experiment. So Planck has a huge beam, was 5 arc minutes, so we had to smooth it to 10 arc minutes to get the right signal to noise. So there's the smoothing by the size of the Planck beam, and there's the smoothing that can come from the fact that the line of sight that you're sampling with dust polarization is much deeper. You're basically seeing all of the dust behind the molecular clouds. So we wanted to check if we still got similar results. So to make a long story short, this is what we got. So we did 4 molecular clouds. All of them are within 160 parsecs from us. There's Taurus, the Pipe, there's Lupus, and Mosca. And by the way, this is very important to link what we have been talking about the whole day and these scales. So if I put a dot here, actually I think the region that Jose Miguel was mentioning this morning would be as big. I cannot point very steady, but the size of that dot would be around the size of the magnetic fields that they are sampling with karma, with the VLA. So this is the kind of comparison. It would be like trying to guess how much money you have in your pocket with the GDP of the country. So it's not directly relatable. We have a gap in scales that we're trying to compare. But in these scales, we see that the dust polarization is sampling more or less the same thing as the starlight polarization. And we see that the directions that you can infer from a starlight polarization lie within 5 degrees of those that we get with Planck. Okay? You can do exercises like this. So you make a vicinity that has the same diameter as the Planck beam, and then you check for what is the dispersion of the field and what is the difference of the field. So we see that there's turbulence inside of the field. So here is just the dispersion of orientation angles. And here's the difference between orientation angles. So you see that you can go to very high values, but in general, the agreement is very large. And what is more interesting, this behavior of the fluctuations in angle within a Planck vicinity, Planck beam size vicinity, and the fluctuation in the polarization fraction, this behavior can be due only to turbulence. If there was a change in the dust polarization properties and dust grain alignment, you wouldn't see such a trend. You wouldn't have correlation between the changes in the polarization fraction and the changes in the polarization direction. So all of that is in the paper, or we can talk about that later. But let's go to the second aspect that I wanted to touch on is, well, this is the agreement in terms of the structure function. But let's move on. I don't have much time. So the second thing that I wanted to tell you today is this seen in other molecular clouds? So we pretty much exhausted all of the molecular clouds which are near to us. So if you want to do the same experiment, you would have to go to higher resolution. And actually, that's how the whole story began. I was working in this polarimeter that didn't work in the first time, and I ended up doing the comparison simulations, preparing for when this was ready. So guess what? Now the blast pole observations are ready. We flew in 2012, and we're going to have a talk about that in the next session by Laura Feso. And same experiment, no? But what is happening there? So the resolution of blast pole is 5 times better than the resolution of Planck. And we observe a cloud that is 5 times further away. So in essence, we're comparing similar scales. And in this cloud, that is in the Vila molecular ridge, we observe polarization in 3 different frequencies, which are represented here by the 3 different colors in these plots. And we see that there is a change in relative orientation from, I wouldn't dare to say mostly perpendicular, because actually this is consistent with no relative orientation, to mostly perpendicular. So from no preferential orientation to mainly perpendicular. And actually that signal is dominated by the 2 structures there, which have the highest column densities and which are represented by ridge. So we see a similar effect in this one. So I see that Chris is standing up. So we have to prepare for when we have more statistics, and we have to understand what is causing the relative orientation. So I'm working with Patrick and Evel, and if you cannot observe all of the clouds that you want, you can at least simulate it and get ready for when you observe them. So by the way, Patrick says hello. And he's producing this 1 kiloparsec box with multiple supernova explosions. And from there, we're handpicking some molecular clouds. We can talk about what is a molecular cloud, but for now, it's just correlated, coherent structures that have a particular column density. And what is interesting is that this simulation covers a very wide range of scales. We're going from the 1 kiloparsec to resolutions of 0.015 parsecs. Okay, so just to give you a brief look of how that feels, this is some of the structures that we selected. Now we're relating the change in the relative orientation with the scaling of the magnetic field, but I don't have time to talk about that, so I'm just going to go through how it feels to go that high in a scale and higher. When we start seeing that things start rotating, become smaller, and this is the resolution of this image. Okay? And with that, I leave you with my conclusions. Thank you.
Thank you very much. Questions? Yes, chat.
Excellent, as always, Juan. I talked a lot with Enrique about this. I suppose I'm being the gravity advocate for 5 seconds. We can talk about this more in the discussion section. But in the rarefied stuff, the non-dense stuff, say you're dragging the field, which I think you probably said at some point in the talk, then assuming a kind of strong field case, you get the nice perpendicular filamentary structure in the magnetic fields. But that's all presumably kind of the same field, right? So it's field's dragged here. Then all of a sudden, is it strong in the filament? Is it really dynamically important? Do we still have an answer to this?
So something that we're seeing in the simulations, again, it's a simulation, so it may be biased by the condition, is that if you have multiple supernova explosions, those accumulations of material can be caused by these flows, by these shocks. And these shocks may be actually favored in the direction parallel to the field line. So in essence, this simulation is like repeating the experiment that Evan Tormusi was showing before. Remember those two colliding shells? Well, this is many colliding shells. So what we're seeing is that those accumulations are actually favoring the direction of the field lines, and that most likely is what is happening.
Which means the field lines, even in the non-dense stuff, are important in a sense.
Yeah.
Okay, any more questions? If not, let's thank Juan again.
Just really quick about the change in the relative orientation in your papers, it happens over a very, very fine column density range. Do you see the same thing in the observations, and do you have any explanation for why it's such a very sharp and fine column density transition that you get this shift in the histogram?
That is a good question. I have the answer of why is it progressive, and it's the fact that everything is correlated, and it would be a matter of the binning. If we had more observations and the binning could be finer, maybe we would see a transition that is smoother. But for now, since we have such coarse binning, from one column density bin, you go to the next one, and it's already perpendicular. So it could be that. So it could be related to the binning.
Okay, now we can thank Juan again.